In current electricity topic, solving the circuits is very important at JEE level. For that, one need to know about the applications of Kirchhoff's laws. Let us now discuss in a detailed way how to apply Kirchhoff's laws in solving different circuits. In fact, we all know Kirchhoff's laws. The very first law is called law of currents. The statement is this: the algebraic sum of currents across any junction point in a circuit, that will be 0. What do you mean by algebraic sum? If you consider the currents which are incoming over there at that junction are positive, then the currents which are leaving the point are to be taken negative. Now, in this particular case, sigma I is equal to 0. In other words, one can say the sum of incoming currents is equal to the sum of outgoing currents as such. So, if I take a small example like this, there is a junction here, a part of the circuit we are taking up here. Now, few currents are just entering and few currents are leaving the same point O. If I consider currents I1, I2, I3 and I4 are entering the circuit, that particular point O in a circuit, whereas I5 and I6 suppose are leaving, then the sum of incoming currents is equal to sum of outgoing ones. So, how to write this equation? I1 plus I2 plus I3 plus I4. I am taking incoming currents as positive ones. Now, minus I5 minus I6, that now becomes 0. That only we can rewrite it like this: I1 plus I2 plus I3 plus I4 is equal to I5 plus I6. In other words, you can just reiterate the same like this: sigma I is equal to 0. That in other words, we can say the algebraic sum of currents across any junction in any circuit, that will be 0. One theoretical importance of this equation is this: it is a direct application of law of conservation of charge. So, theoretically, one should remember this is according to the law of conservation of charge. That is the importance to the first law of Kirchhoff. Now, come to the second one, that is law of networks, we can call it. In other words, you can even call the same as law of EMFs. What is this statement once again? The algebraic sum of EMFs across a closed electrical network, that remains 0. The algebraic sum of EMFs across a closed electrical network, that must be 0. In other words, you can write the same equation as sigma IR is equal to 0. According to Ohm's law, V can be written as I into R, I being the current there, R being the resistance. So, sigma IR is equal to 0. That is actually the statement we can give, or the equation for the statement of second law, that is law of EMFs or law of networks. Now, while taking up this equation, how to consider the direction of current, that matters. In fact, we have a condition like a conventional sign for current is to be taken up. What is the convention we follow generally? When current is flowing in one direction in a circuit, when we are also taking the network in the same direction as that of the current in the circuit, then that current by convention will now be taken with a negative sign. If suppose we move against the direction of current, then we consider that current as positive. What is the reason for this? Whichever point we people are reaching in the circuit, about its potential, if you can understand, according to the potential of that point where you are reaching, we used to just give the convention over here. Suppose if you are going towards a point which is at lower potential than the other point, then you can say that current is to be taken with a negative sign. Suppose if you are going towards higher potential side, then that current is to be considered as positive. So this is one convention what we generally apply while taking up the second law of Kirchhoff. If I just give you a small circuit like this, let us consider here three resistances are now connected in parallel across a cell like this. This is a small circuit which all of you can directly understand easily. R1, R2 and R3 are three resistances which are now connected in parallel. Now the direction of current, of course, will be I here, that enters here. After reaching this junction, current now splits into three different parts. Let us consider the current across R1 as I1, the current across R2 as I2, the current across R3 as I3. So three different currents we are considering in such a way that the sum of all the three currents must now be equal to the total current that is entering into the circuit. So if you say at this junction current is split into three different branches, whereas at this particular junction once again all the three currents they reunite to give the total current as I. So what happens in this? The current that is coming out of the system, that again is going to be I only. That means I is the current entering into the system and I itself is the current which is leaving at the other end. That means the total current in that circuit will not vary. But individually, when you look at this resistance R1, the current across this resistor is I1, across the second resistor is I2, across the third resistor it is I3 as such. Now the question is, while applying this second law, let us name these points like A, B, C, D. This point I take it as E, this is F, this point as G and this point as H. Why we people are naming these points? One should understand first of all, to apply second law, what is a closed electrical network? When can we call that network as a closed one? What is the condition that is needed for that? Let us consider in this circuit A, B, C, D, A is said to be one closed network. That means what? You start from any point. If you can reach the same point without any obstruction in the middle, you can take that one for granted as if it is a closed network. For example, if you start from A, if you go to B, then to C, then to D and come back to A, this is a closed electrical network or a circuit. Such a type of closed networks, if you count in this circuit, you will be finding 6 by number. Look at these 6. A, B, C, D, A is one closed network. A, D, E, F, A, the second one. B, C, E, F, B, the third one. These are 3 internal circuits. Let us now check the external part of it also. If I take that A, B, C, D, G, H, A, this is one network. A, D, G, H, A, that is another network. Similarly, A, F, E, D, G, H, A, that is another network. So totally if you count them, around 6 closed networks we find in the circuit. You can take any circuit which is closed there, any individual network which is closed there, and you can apply second law of Kirchhoff for that. Let us now analyze that one. Let us analyze these networks now applying the second law of Kirchhoff, that is law of EMFs. Check the first network here. A, B, C, D, A is a closed network now. A, B, C, D, A. In this network, when I just move from A to B, I am just following the direction of current. In such case, current is to be taken with a negative sign. When I move from B to C, I am again following the current's direction. In such case, that current is to be taken with a negative sign. When I just move from C to D, in the same manner, current I1 is to be written with a negative sign. When we come back from D to A, I am just moving against the direction of current I2. In such cases, we used to take that current with a positive sign there. So here the current is negative, here current is negative, here also current should be taken negative, and here we can take positive. But in this regard, if you observe carefully, AB is that branch in which there is no mention of any resistance separately. Thereby, I into R, the product of I and R across AB can be taken 0. Exactly in the same manner, across CD also there is no mention of resistance. Therefore, the product of I and R will be 0 there also. So, no need for us to consider AB and CD because the product in each case as I and R is 0. Only thing we have to check is BC. So, how to write that product over here? It is minus I1 R1. In CD it is 0 plus I2 R2, that is equal to 0. It is nothing other than sigma IR is equal to 0. So, sigma IR means here I1 R1, here I2 R2. According to the convention, minus I1 R1, here plus I2 R2, that sum of course must be 0. Now, you can rewrite the same this way as I1 R1 is equal to I2 R2. This is actually the outcome what we can expect from the first network what we have considered. Likewise, let us analyze one more network here. This is A, D, E, F, A. I take A, D, E, F, A. This is the one which I am considering as a small network again. In AD, current is to be taken negative. In DE, current is there, but since no mention of resistance in that particular branch, IR will be 0. EF, when we are moving against the direction of current, I should be written with positive sign. Likewise, FA, the product of I and R will be 0. So, how to write in this particular network? Now you check it. Minus I2 R2 plus I3 R3 is equal to 0. So, what I can write now in this case? I2 R2 is equal to I3 R3. This is the outcome as far as second network whatever is considered here. AD EFA, that is the one. Look at the next one. Suppose if I take BC EFB, BC, EFB. Directly now you can write. In BC, it's minus I1 R1. In CE, value will be 0. Plus I3 R3 that you come across in this case EF is equal to 0. So what do you find once again here? I3 R3 is equal to I1 R1. Just look at the order carefully. Here I1 R1 is equal to I2 R2. Here I2 R2 is equal to I3 R3. Here I3 R3 is equal to I1 R1. So overall what we can understand from this, I1 R1, I2 R2 and I3 R3, all the three are equal. All the three are equal means, is it not individually equal to the value of voltage applied across? So we can say this is equal to V. So this is the outcome of solving all the three different networks which are closed by nature. Exactly in the same manner, let us just analyze at least one network from external circuit. Now AB, CD, GHA, let us analyze that network now. It is AB, I am taking up AB, CD, GHA. This network I take. If you see carefully, in AB, value of IR will be 0. In CD 0, in DG 0, in HA 0, only here we have to calculate and here we have to calculate. Only two values. So if you check in the first case, that is in BC, it will now be minus I1 R1. And of course, while moving from G to H, we are crossing the cell. While crossing the cell, you have to remember the convention this way. When you are crossing the cell from positive side to negative side, positive terminal to negative terminal, then you should consider that potential with a negative sign. If you are crossing from negative side to positive side, then we consider that potential to be positive. So if you check here, I am crossing between G and H, from G to H. That means I am crossing this cell from negative terminal to positive terminal. Therefore, automatically we should write that one as V, and this sum must be 0 according to that law. So what I can directly write from this one, I1 R1 is equal to V. That is the outcome as far as this closed circuit that is concerned. Exactly like that, if I take ADGHA, then you surely can understand I2 R2 will be equal to V. Similarly, if I take AFEDGHA, I will be finding I3 R3 is equal to V. So what ultimately you can get again? I1 R1 is equal to, I2 R2 is equal to, I3 R3 is equal to V. This is actually the outcome even if you analyze all the three possible external circuits. So what ultimately we have to remember as far as Kirchhoff's laws they are concerned. First and foremost, they are easy to apply and they will make your calculation much easier. You can analyze the entire circuit by parts. And second aspect, that first law is a direct application of law of conservation of charge, whereas the second law is the law of conservation of energy in this case. So Kirchhoff's second law is the direct repercussion of law of conservation of energy. And how to just take the conventional signs, if one is thorough with them, automatically you can solve and analyze any kind of a circuit, however big that is going to be. So this is the major application one should remember as far as Kirchhoff's laws they are concerned. So as an application of Kirchhoff's laws, if you just recollect few cases, like few examples where we apply Kirchhoff's laws directly. One of the cases we have is the concept of Wheatstone bridge. When we say Wheatstone bridge, this Wheatstone bridge is a direct application of both the laws of Kirchhoff. And in this one, making use of this bridge, we can calculate unknown values of resistances. Unknown values of resistances we can directly estimate by using or constructing Wheatstone's bridge. When you take this Wheatstone bridge, you will be finding 4 branches this way. Across this one, you know, there will be a galvanometer. Across the other 2, we will be finding a cell that is connected this way. Now you can directly estimate this way the total current if it is entering as I. After reaching this point as A, this I take it as B, this I take it as C, and this one as D. This current now splits into 2 parts. When I consider this resistance as P, this resistance as Q, this one as R and this one as S, you now can understand the current across P as I1. This I1 after reaching here to this point B, that now splits into I2 and IG respectively. Now I2 travels all the way, I3 travels all the way across G. This if I consider the current as I3, this I3 reaches this point D, along with IG, both will mix up to give out the total current as I4 across S. Now this I2 and I4 put together, they give out the total current as I, which of course is entering from here. Same will exit from the other end. Every one of you can identify directly this bridge. In this, 3 of them are known resistances and 1 resistance will now be unknown. That unknown resistance of course can be calculated constructing this Wheatstone bridge. So what is the basic principle here? Try to just recollect. Whenever the bridge is perfectly balanced, then the current across the galvanometer becomes 0. So what we should understand here, when the current across galvanometer, that is IG, is equal to 0, then the balancing condition for Wheatstone bridge can be written as P by Q is equal to R by S. P by Q is equal to R by S. That is one way. The same of course in terms of currents also you can write like this. I1 by I2 is equal to I3 by I4. Like that also you can write I1 by I2 is I3 by I4. In fact, I1 and I2 are going to be equal. I3 and I4 are going to be equal when galvanometer current is 0 or current passing through the galvanometer is 0. So if you take this P by Q is equal to R by S as balancing condition, from that the unknown resistance S now can be determined. That is the advantage of constructing a Wheatstone bridge in general. So in this case, when you just take, there are several closed networks. Once again, we consider a closed network like ABDA, second network like BCDB, likewise the third one if you want ABCDA, like that 2-3 networks you can analyze to obtain this particular formula. In fact, this is a very important equation for every one of us to remember as far as the calculation of unknown resistance that is concerned. So the only point we have to remember here is what is the balancing condition for this. And when can we apply that balancing condition? The balancing condition is that the galvanometer current should be 0. Then we can directly write P by Q and R by S are equal. Thereby the unknown value of resistance that can be estimated directly. That is the advantage. Now what is the only theoretical point you have to remember here? When you interchange the galvanometer and this cell, when we interchange the galvanometer and this cell, will there be any change in the balancing condition of Wheatstone bridge? That's what is a question. Now the answer for that one is there will be absolutely no change. So even if we interchange this galvanometer and this voltage with this potential difference, the source of potential difference, that is the cell, even if you interchange them in their positions, there will not be any change as far as the balancing condition that is concerned. Using exactly the same condition, balancing condition, we have just taken a meter bridge here. What is this meter bridge and what for it is being used? Two things we have to remember. One, to calculate unknown values of resistances. Using meter bridge, unknown values of resistances you can determine. And what is the second one? The second use of this one is you can determine resistivity of a wire. That is of course a conductor. Resistivity is also called a specific resistance. So here we people are taking up a conducting wire. Whatever is the material of that wire, for that material you can determine the resistivity part of it. When you just take this meter bridge, how this looks like? You will be finding on a wooden base, 3 metal strips are mounted this way. You can understand directly. On each strip, 3 connecting screws we will be finding, and we used to have a meter long wire connected in between these two. This now is connected across a cell and a cell, this one key like this. This is what is called as primary circuit. This primary circuit. And this is what we call it as left gap of meter bridge, and this one is the right gap. In the left gap, we connect a resistance box. In the right gap, we connect that wire of which the resistance is to be determined. From this particular screw or connecting terminal, we connect a high resistance and a galvanometer, and there from it's connected to a jockey like this. And in fact, this circuit we call it as a secondary circuit. Now what one has to understand from this one is, if unknown resistance if you take it as R1 and known resistance if you take it as R, you can determine this value of R1 by the same application of balancing condition of Wheatstone bridge. So in the resistance box, when we apply some known resistance, the balance length of course we used to measure as L1 here, and the remaining length of course when I consider it as L2, the sum of these two values L1 and L2 must be equal to 1 meter of this wire. That in the sense the total length of this wire is exactly a meter. If L1 comes to be 40 centimeter, L2 automatically will be 60 centimeter, we know that. Now what is the principle of this particular Wheatstone bridge? Same principle we have to apply here. Same condition is to be taken up there. How just do you look at R by R1, that is this known resistance by unknown value, that now must be equal to L1 by L2. This balance length whatever we are obtaining it as L1 and this one as L2, this R by R1 is equal to L1 by L2. In fact, this is the equation by means of which this unknown resistance R1 we can calculate using meter bridge. But one thing one should understand, meter bridge is a simplified form of Wheatstone bridge. There is absolutely no difference between these two. We are taking up lengths over here. Why we are taking instead of resistances the lengths, like theoretically speaking, resistance is directly proportional to length of the conducting material, conducting wire. Therefore, we can say R by R1 is equal to L1 by L2, where L1 comes to be the balancing length in meter bridge. So this is one more application of this Wheatstone bridge in the form of meter bridge, you people have to remember. So this is one. In the same chapter, we have one more instrument by name potentiometer. What is its use? First and foremost, it is used in measuring the EMF of a cell. It is used to compare EMFs of given two cells. It is even used to determine the internal resistance of a given cell. So there are three different areas you have to concentrate as far as this potentiometer that is concerned. What is its principle? First of all, potential gradient that remains constant. What do you mean by this potential gradient? That of course we can write it as dV by dx. That now must be constant here. In other words, you can even say, if E is EMF, EMF per unit length of the wire, that remains constant. So when you just take this potentiometer, it will be having a wire of length around 8 meter, 10 meter, 12 meter, like that. And in fact, we all know, more is the length of the potentiometer wire, more will be the sensitivity of that instrument, more will be the corresponding accuracy of that instrument. So that is one area you have to concentrate much on. Now the second point over here, when we consider this potentiometer circuit, you will be finding one circuit again is called as primary circuit. This primary circuit is going to have a cell of greater EMF, and secondary circuit whatever we are finding here, that now will have a cell of EMF E1 which is to be determined there, and that again is going to be connected to high resistance, then to galvanometer, and that galvanometer is directly connected to the potentiometer wire. It can in fact slide over by means of a jockey. Now if you just look at this is primary and this one is secondary, one point we should understand, voltmeter and potentiometer both are going to be used to determine EMF only, but potentiometer is preferred more. What is the reason? For that one theoretical aspect you have to remember. Potentiometer will never extract current from the cell connected in the secondary circuit. When potentiometer is not extracting current from the cell in the secondary, automatically the EMF of that cell can be determined with utmost accuracy here. So definitely potentiometer is much more accurate than a voltmeter. So this is one theoretical aspect one should remember. Come to the second one. What exactly are the different equations of potentiometer? I'll simply remind you. When we are taking up one cell connected here as of EMF E1, let us take the balance length here is L1. Then what I can write here? E1 by L1 will now be a constant. Suppose if I replace this one by another cell of EMF E2, and if I get the corresponding balancing length as L2, then I can rewrite the same equation this way, E2 by L2, that now becomes a constant again. So what exactly is the equation we can produce? E1 by L1 must be equal to E2 by L2. Then what would be the way of comparing the EMFs now? E1 by E2, which is the ratio of EMFs of two different cells, is equal to L1 by L2, we can directly write. L1 is balancing length when first cell is connected in the secondary circuit. L2 is balancing length when second cell is connected in the secondary circuit. Now the same experiment you can perform in a different way also, which gives a different other equation for us to determine the ratio of EMFs of two given cells. Just in the secondary circuit, we are connecting both the cells in series. For example, one is of EMF E1, one is of EMF E2. Both are now connected in series across the secondary circuit. After that, after connecting them like this, we have calculated the balancing length as L1. Then what to write over here as an equation? E1 plus E2 by L1 must be a constant. That is, potential gradient is constant again, we can write. Now, one out of the two cells, you reverse that one. That means what do you find here? One cell is connected regularly and other cell is reversed. If I write its EMF as E1, its EMF is to be written with a negative sign there. Thereby, what is the corresponding length, balancing length after connecting this one over here in the secondary circuit? Again you calculate the balancing length. Suppose the balancing length is L2 this time. Then what can we write? E1 minus E2 by L2 is going to be constant now. Now, if you equate these two, what is the ultimate outcome you can get? E1 plus E2 by E1 minus E2 will now be equal to L1 by L2. That only you can apply by taking componendo dividendo. You can write E1 by E2 is equal to L1 plus L2 by L1 minus L2. This is another formula by means of which you can compare the EMFs of two given cells using potentiometer. So, two different equations you have to remember. Applications on both the equations you will find, and particularly the second one is one of the very important concepts for you to remember. Now, in the same manner, how can we directly calculate the internal resistance of a given cell using a potentiometer? That time, of course, to the same cell, whatever we are connecting it here, the cell whatever is connected here, across that one we connect an external resistance R, and there is another key that is provided here. The remaining system will be as it is. You will not find any variation as far as the circuit that is concerned. But what we have to understand here is, when you put the key in, then the resistance also takes part in the circuit. When suppose key is plucked out, then only this cell that takes part in the circuit in the secondary as such. Therefore, what we do in this particular case is, without the application of external resistance, we just determine whatever the balance length that is observed as L1. So that means when E1 is connected across the secondary circuit, L1 is the balancing length, for example. That is, without the resistance it is L1. Now put the key in, then the circuit will have external resistance also connected in the system. Thereby, whatever the length, balancing length we are getting, that you take it as L2. That means without external resistance, balancing length is L1. With the external resistance also connected, the balancing length you take it as L2. Then what is the internal resistance of this circuit? That is the question. R is equal to L1 minus L2 by L2 into R. What is this formula out of it? You just check it. L1 is the balancing length when only the cell is connected in the secondary circuit without the external resistor. L2 is the balancing length when the resistance also is taking part in the circuit, that is the secondary circuit. And capital R stands for the external resistance what has been connected over here. Thereby, if you use this formula, you can directly get the internal resistance of the cell which is connected in the secondary circuit as such. So potentiometer, whenever we want to take up, three major equations one has to remember for any entrance exam, that is including JEE. If you take E1 by E2 is equal to L1 by L2 is one equation. E1 by E2 is equal to L1 plus L2 by L1 minus L2 is another equation. Likewise, for internal resistance of the cell, it is L1 minus L2 by L2 into capital R. These are the three different equations one has to remember as far as potentiometer and its application that is concerned. Let me now remind you few cases where we directly apply the concept of Wheatstone bridge. When we have three resistances connected like this, one more resistance connected this way, another resistance is connected like this. Let us say this point as B and this point as A. Each resistance you take it as R. All the five are of the same magnitude. Now this circuit, if you look at carefully, it is an application of Wheatstone bridge. You can see this one as the first branch, this one the second one, this one the third, this one the fourth, and this one is the resistance which is in place of the galvanometer. And another important feature, whenever in a Wheatstone bridge, if all the four values of resistances are equal, same value will now be the resultant as well. Now here what you should understand, these two are in series, these two are in series, and this resistance does not carry any amount of current. So automatically we can understand when these two are in series, the value will be 2R. These two are in series, the value will be 2R. When both are now in parallel, the effective resistance in this case will now be equal to R like. So whenever we consider a Wheatstone bridge in this form, you directly can estimate that these two resistances are going to be in series, these two resistances are in series, and both are now going to be in parallel. That is the concept one should understand. Now the same Wheatstone bridge even can be drawn this way also. One more example I will just give you. This is the case of an equilateral triangle having all the three sides, three resistances like this. One more resistance is connected across these two, the centroid and this end, one more here, one more here. Even this resistance circuit, if you take this one as R, this one has R, this has R, this one, this one, this one. Each one is R like. Then also you can see, barring this resistance, you will be finding a Wheatstone bridge. Suppose if they are different by any chance, R1, this is R2, this is R3, this is R4, this is R5 and this one is R6. Suppose if they are different, they are all same means directly we can understand like this. If they are different, then what must be the condition for us to identify that one? R1 by R2, that must be equal to R4 by R5. R1 by R2 must be equal to R4 by R5. By any chance if this is true, then you can understand no current that flows across R3. When no current that flows across R3, R1 and R2 are said to be in series, R4 and R5 are said to be in series, and both are in parallel as far as Wheatstone bridge that is concerned. That entire Wheatstone bridge is now parallel to the other one also, that is R6. So what we should understand here now, R1 and R2 are in series, then what would be the effective value? It is R1 plus R2. And R4 and R5 are in series, the effective value will be R4 and plus R5. They are now in series. Now when both are in parallel and parallel to R6, then how do we write that formula? 1 by effective resistance, that is equal to 1 by R1 plus R2 plus 1 by R4 plus R5 plus 1 by R6. This is the way we people used to take up the effective resistance in that circuit. So when resistance circuits are given, if the circuit is consisting of a Wheatstone bridge, calculating the effective resistance is going to be a very simple concept. But one should identify where exactly that Wheatstone bridge is located. If you can identify that one, automatically you can estimate what is going to be the effective resistance across that. But in some cases, that particular circuit looks like a Wheatstone bridge, but it will not be a Wheatstone bridge. That means it will not directly obey the condition for Wheatstone bridge, which is called the balancing condition for Wheatstone bridge. In such cases, one should apply Kirchhoff's laws and solve the circuit as such. So those problems also one should be careful enough, and those applications also one should be thorough enough. Then only the application of Kirchhoff's law can be worked out easily in the final examination as such.